Hello, everyone. My name is Runzhi Zhang. I'm a PhD student at the University of Florida. So my topic today is adaptive sparse multi-block partial least square for survival prediction using multi-omics data. So firstly, I will introduce the background, and then I will talk about the details of our methods, asmbPLS, which is a PLS-based method to do the feature selection and outcome prediction for continuous outcome. And finally, I will briefly introduce our package for the method. So with the development of high throughput studies, we are able to generate omics data on a large scale fastly and cost effectively. Different types of omics data, for example, genomics, transcriptomics, and so on, have enriched our understanding of the mechanism of different disease. And because of the high throughput technology, there exist more and more patients with different types of omics data available for the same patients. Therefore, the research interests have gradually moved from single omics analysis to multi-omics analysis. So for multi-omics analysis, the dataset is always structured in blocks, where each block represents variable from a specific type of omics data observed on a group of individuals. Usually, multi-omics data has several important characteristics. First one is high dimensionality. It means that number of features typically vastly outnumber sample size. Two is sparsity. Some features are detectable in only a minority of samples. And third, there exists correlation between features across different blocks and also within the same block. So each type of omics data may contribute unique information. Integration of omics data may provide us with some new perspective and also enable us to understand the complex relationship between the omics data and the host. And based on the multi-omics data, we'll be able to build a prediction model with good accuracy. And in turn, we can use the model to predict the outcome we are interested in. There are some real problems that using multi-omics data can help. The accelerated linear time AFT model is considered here. In AFT model, suppose T denotes time to certain event of interest. We model a transformed Y equal to log T on a set of covariates using linear regression. Survival time for subject I can be presented by Ti and delta I. Delta I equal to 0 here indicates the censored subject. Since the true survival time are not available for the individual with delta I equal to 0, the general prediction method will not apply. In addition, ignoring censored subjects would cause a prediction bias, and reducing sample size also results in loss of power. To handle this, we propose to replace yi by imputed y, such that it has the same mean function as yi and also is computable from the observed data. In this study, mean imputation is used to this end. And a multi-block partial least square can be used for this purpose. So the in multi-block PLS and BPLS, that input metrics including B blocks indicate different omics data, and block Y. So these two be predictor matrix and outcome vector on the same n samples respectively. And the goal of the asmbPLS algorithm is to find the parameters that maximize the covariance between two summary vectors, TTJ and UJ for J's PLS component. So for here, the TTJ and UJ are two latent variables containing the information from X and Y respectively. Therefore, the problem is formally expressed as follows. So for J's PLS component, the dimension reduction is implemented by taking a linear combination of the variables to obtain the block scores TBJ in each block. So where WBJ here is XB block variable weights that express the relevance of variables, which is obtained via the algorithm. And MXB here is the number of variables in XB block that is used for block scaling. And after calculating the TBJ for each block, we combine all blocks scored in a new matrix, TOJ, which include information from different blocks. Then the dimension reduction is conducted again by taking a linear combination of different block score to obtain the super score, TTJ here, which summarize variable information from different blocks. And similarly, UJ is a summary vector of Y. Once all the parameters are calculated for the first PLS components, we can do the parameters. We can do the deflation and then do the same step for the second PLS component and so on. And more details will be discussed in the next page. So we start with the original X and Y, and we obtain the parameters for the first PLS components. And X and Y are then deflated. Information already used are removed from the original data, and the deflated X and Y are used as the input for the next PLS components, and so on. And the optimal number of PLS components can be decided via cross-validation. And sparse multi-block partial least square here is a sparse version of asmbPLS. It can be achieved by adding a L1 penalty on each weight vector, WBJ we mentioned before. And in asmbPLS algorithm, penalty factor lambda b is fixed for all of the PLS components in blocks. However, when all the weights in block B are smaller than the lambda b during the convergence iterations given inappropriate lambda b, all the weights will shrink to 0, resulting in no information of block B included in the superscore TTJ. So therefore, block B cannot provide any information for the prediction. And in addition, lambda B is not necessarily the best penalty factor for all the PLS components in block B. So based on this, we introduce our proposed methods, asmbPLS. Different from sparse asmbPLS, we use quantile of the weights as our penalty factor. So in this algorithm, quantile is a function to obtain the corresponding quantile of the absolute weight, and sparse is a soft thresholding function that is used to optimize the objective function with lots of penalties. So using the quantile function, we can always find the reasonable lambda bj that help us to retain the most relevant variables. And combine these two functions, we aim to find the best quantile for each PLS component in each block that maximize the prediction performance of the proposed method, and also the feature selection. Furthermore, by doing this, the explanation for the retained variables can be more straightforward. For example, if you set quantile to 0.9, it means that only the top 10% of the features will be retained. So for each block, we want to know how many features are the real relevant features. We can try with different quantiles, then we will have different quantile combination for the blocks. For example, when let b equal to 2 and the number of PLS components equal to 5 here, then we have some prior knowledge that only a small proportion of features in block 1 are relevant. So we can set quantile to 0.9 and 0.95 here. You can see in this plot. And for block 2, we don't have any idea, so we can give a wider range from 0.2 to 0.9. So then we have 10 combinations. So k-fold cross-validation is used to help us find which combination gives us the lowest MSE. MSE here is the mean square error. Then this combination will be used for this PLS component, and then we can move to the next PLS components and so on. Finally, we will find the best quantile combination for each PLS component. And we can also use the results of the cross-validation to find the optimal number of PLS components used in our model. So also, we start from first PLS component. If including one more PLS component, will it decrease MSE by 5%. Here, then we will include one more. Based on this, we can get the optimal number of PLS components used. We may fit the model using 5 PLS components, but we are not necessary to use all the PLS components for the prediction. And so we will use the simulated data and the real data to test the performance of the methods. So for this simulated data, we will simulate microbiome data and metabolome data and survival data. And for the real data is melanoma patient data. We have 89 samples with around 40% sensor rate in the real data, and we have 3 different types of data, predictor blocks. Here is the structure for the simulated data. So we have N samples and Q microbial taxa and P metabolized, and also we will simulate the patient survival. So microbial data is simulated based on directed multinomial distribution. Once it's simulated, microbiome data will be used for simulating the metabolome data. For here, metabolome data is consisting of 3 parts. One is the intensity of each metabolite, and microbiome effect on the metabolites and the error term. And different value of A here indicate different scales of association between microbiome and metabolome data. So which is the coefficient of the microbiome feature. And once the microbiome data and metabolome data are simulated, survival data is simulated based on these 2 omics data. So we net survival data to survival time to follow log normal distribution or Weibull distribution. And betas here are used to indicate the effect of microbial features and metabolite on the survival time. And R here indicates different level of noise. So we have different settings for our betas. In setting 1, there are only several relevant features in both blocks. And in setting 2, for both blocks, the coefficients are fast decaying with only a small proportion of features contributing to the outcome. Setting 3 is similar to setting 2, but with a slower decay. And setting 4 corresponds to the situation where all the features have equal contribution to the outcome. And in setting 5, there are different number of relevant features in different blocks. So where number of relevant taxa is larger than the number of relevant metabolites. Setting 6 is similar to setting 5, but with a number of relevant taxa smaller than the number of relevant metabolites. And in the previous step, we simulate the true survival time, but we want some of our samples to be like ret censored. So here, C is simulated and added to the true survival time to generate the censored survival time. For example, if censoring rate is set to 0.5, we want that half of the C is smaller than 0. And this 50% of the censored survival time will be smaller than the true survival time. So the sensor, so based on this, for this 50%, the sensor survival time are observed. And we set sensor rate to be 0.1, 0.3, 0.5, and 0.7. And also, we have set different number of features in different scenario. We have low dimension where Q and P are both equal to 200, and also the mixed dimension where Q equal to 1000 and P equal to 200, and also the high dimension where Q and P both equal to 1000. And all the implementation were conducted using R in the Hypergator 3. Hypergator 3 is a high performance computing cluster at the University of Florida. And we include several competitive algorithms for compression purpose. This method all consider the group structure of the data and can do the prediction. We'll compare the performance of algorithm in 3 aspects. First, prediction performance. Second, feature selection. And third, computation efficiency. So here is the summary of all the scenario. So we have different dimension setting and different association between the two predictor blocks, and different scale of noise and different scale of sensing rate and different survival time distribution, log normal and Weibo. And for the relative abundance, since the microbiome data is, we will use the relative, it always used as the relative abundance. So for microbiome data, we'll impute 0 value with the small value 0.5 first, and then we'll do the centered log ratio transformation for the microbiome data to remove the value range restriction. And we will set the PLS components to 5 for asmbPLS and mbPLS. And for the low dimension, the quantile for the both blocks will be set. It start from 0.7 and to 0.975. And for the mixed dimension, the quantile set for the first block is from 0.7 to 0.995, and for the second block is the same as the low dimension setting. And for the high dimension setting, both blocks, the quantile setting is from 0.7 to 0.995. So for here, we show the plot here displays the distribution of the number of PLS components used, which gives us the lowest MSE for the prediction. So you can see that in scenario with lower noise, where the x-axis is the different scale of noise, and the y-axis is the different sensor rate. So in scenarios with a lower noise, for example, R equal to 0.1 and 0.2, using the first PLS component. So using the first is marked in red. So using the first PLS component, or the first two is you can see in the plot, or in the first two, gives us the lowest MSEP most of the time. And with the increase in noise, more than half of the lowest MSEs are obtained from using the first PLS component only. So we found a similar trend in other dimension setting also. So this plot is for the low dimension setting. And to comprehensively investigate the performance of asmbPLS, we included 2 versions of asmbPLS for compression. So first is that the number of PLS components is selected based on the result of cross-validation, as we mentioned before. And second, is the asmbPLS using the first PLS component only. So this plot displays the result for low dimension setting, where the survival time is log normal distributed, and the a equal to 2 indicate there high association between the 2 predictor blocks, and A, B, C, D indicate different sensoring rate. So the left 2 are the proposed method, one with optimal number of PLS component and one with the first PLS component only. So in summary, although asmbPLS is not the best in low sensory rate scenario, the performance of asmbPLS of our of the proposed method improves with the increase of the sensing rate, and the overall performance of asmbPLS achieves the highest in high sensing rate scenario. You can see the row here is indicate different scale of noise, and the column indicates the different beta setting. And in addition, asmbPLS performs better in scenario where there are just a few very significant features. You can see it's for beta 2 setting here. You can see the left 2. You can see such lower MSE than the other competitive method. And by comparing the two versions of asmbPLS, we found that asmbPLS with CV performs better in scenario with lower sensing rate and lower noise, but slightly worse with increase of the sensing rate and noise. And the similar trends can be found in other scenarios. And here I take out the plot C so you can see clear. So for beta 4, you can also find that where all the features contribute equally, mbPLS is the best. It makes sense since mbPLS used all the features as predictors, and also mbPLS is a special case of asmbPLS where quantile is set to 0 for both blocks, indicating that all the features are retained. And this plot displays the results of feature selection for low dimension setting. Here, ABCD indicates sensitivity and specificity for different blocks. So for beta setting 1, 4, and 5, 1, 5, and 6, we already know the true level. And for beta setting 2 and 3, we use simple linear regression together, and also the FDR p-value adjustment to get the adjusted p-value, and the adjusted p-value smaller than 0.05, we define it as a significant features. And we can find that with the increase of the noise and the sensing rate, with the increase of the noise and sensing rate, asmbPLS can keep its sensitivity where all the other methods decrease gradually. You can see the red one, the red is the asmbPLS, and the other color are the other method. And correspondingly, the higher sensitivity is with lower specificity. So we have a little bit lower specificity than the other methods. And with the increase of the number of features, we found relatively lower sensitivity and higher specificity for all the methods in nearly all the scenarios for both blocks compared to what we obtained in the low dimension setting. So here, this plot is based on the low dimension setting. So this makes sense since when more features are included with the number of true relevant features unchanged, to obtain the true features will be more difficult. And regarding the computation efficiency, mbPLS is the fastest, and all methods is much faster than the other competitive methods. So these are computation time in seconds. And for real data, we have 89 samples with around 40% sensing rate. Our outcome here is progression-free survival time. We include 3 blocks: microbiome data, Muti-Omics data, and clinical data. They have different number of features, and also the simple linear regression and FDR p-value adjusted are implemented to define the significant features. So for here, we have 0 significant microbiome features, and 0 significant protein, and 2 significant clinical variables. And for the quantile used here, we assume that only a small proportion of features are relevant in the microbiome and proteomics data. So we try with high quantile, you can see here. And for clinical data, we try with wider range and from 0 to 0.99. And the optimal number of PLS component based on the cross-validation is 2 here. So based on the leave one out cross-validation, all methods show the lowest MSE compared to other methods, even though it's just slightly lower than sparse group LASSO and IPF, but it's best in the real data. And for the feature selection, our method retained 6 microbial taxa, 21 proteins, and 2 clinical variables. So you can see we include like even though there's no significant features, we still retain some of features from microbiome block and the proteomics block. This is due to the nature of our methods. Our method will always retain some features for each of the block to keep some information about their relative importance. But however, based on the block width, we'll be able to know which block is much more relevant to the outcome. You can see here the clinical block is a much more relevant to outcome than the other 2 blocks. And for here's the feature selection for the other methods. So some they didn't select much features in the first 2 blocks, but some of them select less clinical variable and some select more clinical variables for the clinical block. And in addition, we explored the utility of the superscore. So superscore is only can be obtained from the partial least square based method. So superscore contains the information from all the blocks and can be used as a predictor for the outcome also. So superscore is significant based on plot. You can see the superscore is significant associated with proportion-free survival time. And patients with a higher superscore which is a blue group here, seem to have much higher survival probability. So in other words, once we have a new sample with its corresponding microbiome, proteomics, and clinical data, so asmbPLS is able to calculate the superscore and then assign the sample to high or low survival group. So this information can help the decision of future treatment. And also, so all of our methods function are included in our package asmbPLS. You can we have upload to the GitHub, so you can install our package from the GitHub, and it will be uploaded to the our grant like soon. And thank you very much. So here's all the presentation. So if you have like question about my presentation, you can like email. You can send an email to my to me, and we can have further discussion. Thank you very much. And here's the reference for the presentation. Thank you so much for listening.